On to problems 9 through 12. We're going to look at the following molecules, so these 5 cyclic molecules, and we're going to try to find some of their unique characteristics. First, we want to know which one has the largest molecular heat of combustion, and that's for the entire molecule. Then we want to know the heat of combustion for just each methyl group. Then we want to know about the entire ring strain, or the ring strain of just each methyl group, and then the entire ring strain of the entire molecule. Okay, so looking at the first one, the molecular heat of combustion of the entire molecule. For this, we want to count up the bonds of all these compounds. So looking at A, we start off with a 3-membered ring, and we progress to 4, 5, 6, and 7. The number of carbons actually tells us the number of bonds. So if we have 4 carbons, we have 4 bonds. If we have 7, we have 7 bonds. And since this one has more bonds, it's going to give off more energy because of all those bonds breaking. So the largest by far is the one with the most C's, so E. The largest one, it's going to have the most bonds. Next, we're going to want to know the heat of combustion for a methyl group. So basically now we're focusing on the bonds breaking individually, not the entire thing. So which one of these bonds are strongest? For this, we want to know about ring strain. And ring strain is going to be the difference from the bonding angles we have up here to the angles, the ideal angle, 109. 109 is where every methyl group wants to be at, or every carbon, because that's the most stable for that compound. So looking at A, we have a 60 degree because it's a triangle. B, we get 90 degrees. And as we get to the bigger polygons like C, D, and E, it's not the same as a normal polygon because they can twist, unlike the square and triangle. So these take into account that they're 3D now. They can twist kind of like D, our cyclohexane, has that famous chair conformation. This allows it to bend a little upwards and downwards using its 3D model, and that makes it be able to get smaller angles than it would normally if it was flat. So the highest, most combustible per first methyl group is going to be the one with the biggest ring strain, because it takes energy for that ring to hold that unstable strain. So the one with the highest difference in the ideal number and the actual is A, because 60 is about a 49 difference as opposed to the square with 90. So the one with the most exothermic per methyl group will end up being A. Now we want to know the largest amount of ring strain. That builds off of 10. We, again, since it's so few membered rings, it's only has 3 carbons, it's going to be A again. That's because, again, the bonds are a lot more unstable than usual, so each one has a lot more energy when you break it. It has a lot more strain because it's so different from this ideal. Lastly, we have which compound has the least amount of ring strain. So then we compare, again, the ideal angle to the actual angles, and the one that's right smack on the money is D, 109. Our answer here is going to be D again.